Um, Hello, everyone. So I'm Echo from University of Florida, and thanks for being here. So today, I guess before we will dive into the modeling stuff, it would be great to revisit how are we doing in actually measuring volatiles in the magma system. And in my part, I will actually focus on the effort that of reconstruction CO2 concentration in the melting inclusion using different methods. And I would also like to thank Daniel Lee, a graduate student from Vermont, Columbia University. So Daniel and I have been working on this topic and using piston cylinder experiments and also in improving the experimental methods which I will show in the slides. All right, so basically, melting inclusion are these little melt parcel that's included inside, entrapped inside the crystal during crystal growth. And very often, the volatile contents of melting inclusions are used to represent the magmatic content, volatile contents, and calculate the total volatile fluxes, and also infer the mental source concentration. And because the water CO2 solubility are very sensitive to pressure, very often melting inclusions are also used to infer the entrapment pressure and where the magma actually are stored, cooled, crystallized, or even mixing. So melting inclusions are also used for review the degassing history of the magma. But all these wonderful applications really rely on if melting inclusions could actually faithfully preserve the volatile contents of the magma. Unfortunately, this is not necessarily the case. After its entrapment, there are several post-entrapment modifications could happen to the melting inclusions. For example, for CO2, this little vapor bubble inside the melting inclusion actually could sequestrate significant amount of CO2 from the melt. And so for this talk, I will first go through how this vapor bubble formed, and then different methods that people have been using to reconstruct the CO2 concentration in the melting inclusions. And lastly, I would like to quickly go through an example of Turrialba volcano, where we actually combined melting inclusion, volcanic gas data, and also degassing model to infer the plumbing system underneath the volcano. All right, so let's just take a quick look at what could have happened to a melting inclusion after its entrapment. So this figure showing is Y is the pressure and then temperature. This blue curve basically showing the melting inclusion could first have been entrapped in a relatively high pressure, right? And during this magma storage period, the melting inclusion could have already undergone a certain amount of cooling. And then during the magma runoff and eruption, ascent and eruption, the melting inclusion would be brought up to the surface. So this is a very simplified scenario, which is an adiabatic ascent. And it could be more complicated than this. And then after eruption, the melting inclusion would experience quench, where the temperature drops significantly all the way until below the glass transition temperature. So reacting to all these external changes, this melting inclusion could have gone through first, upon cooling, the differential contraction between the melting inclusion and the host mineral. And because of cooling, melting inclusion could also start to crystallize, which is very often referred as a post-entrapment crystallization. And then in olivine host melting inclusion, very often you could also have is the melting inclusion exchange iron and magnesium with the host crystal. And also melting inclusion would be losing water through hydrogen diffusion. So all this process overall would actually result in a decrease of internal pressure of the melting inclusion, which is shown in this red dashed line. So because CO2 concentrate, the solubility is really sensitive to pressure. So if we assume the melting inclusion is vapor saturated at the entrapment, the CO2 concentration in the melting inclusion shown in this green curve would actually decrease, and the excess CO2 would go to this vapor bubble. So because the diffusion time scale of CO2 is actually significantly faster compared to all these magmatic process. This is a figure from Rasmussen et al. 2020. So this process is not really kinetically limited, and it will only stop until the temperature drop down to the CO2 closure temperature. Basically, it's too low for CO2 to move. And this temperature is a function of cooling rate, but it overall is actually higher than the glass transition temperature. So that means after CO2 starts entering the vapor bubble itself could still continue to grow due to expansion all the way until the temperature is actually even lower than the glass transition temperature, where all the changes will stop. So going through all this process naturally lead to our first approach, that is actually model one or several of these processes and model the vapor bubble growth and reconstruct the CO2. And there are several models available. So the advantage of this modeling process is that we could actually apply the modeling to all the melting inclusions that we have actually measured before. So for example, this is a summary figure from Kelly and Fisher 2025, where they actually applied mimic one of the vapor bubble growth model to different arc magmas. So the open symbols are the reconstructed CO2. We can see almost for every arcs, it actually gives much higher CO2 concentration compared to the ones that not counting the vapor bubble. However, the downside of the modeling approach is that it involves a lot of assumptions and also uncertainties. And also, depending on the model you're using, one or several processes could not have been actually included in this modeling growth. So it could be an incomplete reconstruction. And not only the model that tells us a lot of CO2 could have gone into the vapor bubble, and we actually see the CO2 inside the vapor bubble using Raman analysis, which naturally led to the second method is actually measuring the CO2 density inside the vapor bubble, and then measuring the CO2 concentration in this glassy melting inclusion part, and then using the volume of the vapor bubble and the volume of the melting inclusion to calculate the total CO2. So this is a figure from Penny's paper. So we can see that regardless of the different setting magma, so reconstruction of Raman show that almost up to 100% of CO2 could actually have gone into the vapor bubble. Another interesting thing for Raman is it would also allow us to actually see other species, other things inside the vapor bubble if they are there. So even though it's less common, for example, there's one study actually have shown that there are sulfur-bearing minerals that in the vapor bubble. Okay, so lastly, we could also reheat the melting inclusion to redissolve to dissolve the vapor bubble back into the melt. Basically, it would be like a reverse process of this diagram. So these have been done at 1 atmosphere, but very often it will actually lead to the melting inclusion decrepitation because it will actually create this huge pressurization for the melting inclusion compared to the hosting mineral. It has also been done at higher pressure, using either internally heated pressure vessel or piston cylinder. So piston cylinder method is the ones I have been using. So we usually will pressurize our samples to 8 to 10 kilobars and then heat it up to the temperature that's above liquidus temperature. Of course, you could also pressurize to higher pressure if you think your melting inclusion actually contains a lot of CO2 and entrapped at higher pressure. And we have also used a calcium fluoride pressure medium that would allow much faster quench compared to the conventional barium carbonate sleeve. And we also include surround the crystals in this molten salt plus hydroxides to minimize the water loss. So overall, the experimental advantage would be successful run would actually result in one single glassy melting inclusion that would allow us to directly measure the total CO2 and sulfur in the melting inclusion without involving too much assumptions or uncertainties. It would also be great, allow us to actually measure the magmatic carbon and sulfur isotope. Otherwise, it would actually be fractionated by the vapor bubble. And for IHPV and piston cylinder, we could actually put multiple crystals in one run, so it potentially can be highly effective. However, because we're actually reheating the melting inclusion, it actually can change the major elements a little bit, which can be actually corrected later. But it also could have changed the FO2 and the water concentration in the melting inclusion. Therefore, we do recommend you also have a parallel set of untreated melting inclusion, especially if you want to constrain the oxygen, fuel gas, and the water. All right, So let's move to a case study for Turrialba. So Turrialba is this open degassing volcano in Costa Rica, where it has actually displayed these two modes of CO2 sulfur ratio in the gas. So basically during the quiescent degassing, the CO2 sulfur ratio is relatively low, but just before eruption, it always increase. Our question is, where do these two modes of gas come from? So we used the olivine hosted melting inclusion from Turrialba, and then we run a rehomogenization experiments in piston cylinder to rehomogenize the vapor bubble. And then here we can see the solid symbols are the rehomogenized CO2, which is much higher compared to the untreated CO2. And then we run guided by the melting inclusions, we ran degassing model to model the CO2 sulfur evolution in the melt and also in the gas. So we can compare to the gas data. Lastly, we also compared it to the geophysical constraints. So just here are the results. So this is the model, the CO2 sulfur ratio compared to the quiescent gas and also the pre-eruptive gas. We see the comparison shows that this quiescent gas could have been derived from the depths between 4 to 8 kilometers, where actually the magma starts to significantly losing water, so and stalling. And then the pre-eruptive gas comes from actually much deeper, between 12 to 18 kilometers, but it also overlaps with the highest entrapment pressure shown in our melting inclusion record. So this is a published study if you're interested in this. But we are also hoping to actually test this hypothesis on other volcanoes, which also display these two modes of degassing. All right, so lastly, I would like to leave you guys with this compilation figure from Daniel, where he actually shows how the saturation pressure of melting inclusions from different volcanoes have been actually increased by counting vapor bubble, either using Raman showing in the yellow symbols or using rehomogenization experiments showing in the blue symbols. So we can see after the reconstruction, this would really allow us to compare our melting inclusion record to the geophysical constraints, and the reconstructed CO2 would also improve our estimate of the CO2 fluxes of different volcanoes. Well, thanks.
Oh yeah, if you want to come say so that well.
It's just some jelly, isn't that right, screen?
Yes, thank you.
We can do a quick question for Echo while we're changing over the PowerPoints if anyone has a quick one, otherwise we'll do more questions later.
I have a quick comment. On that last compilation figure that Daniel made, there was a black line at 250 MPa that used to be considered where melt inclusions decrepitate. And so we know that we've blown way past that. And so I don't think we understand what controls the decrepitation of melt inclusions. It's another really good question.
It's the Mac.
Yeah.
Oh, it's just, do you want to do it? Because I'm not a Mac guy.
It's not a Mac.
What is a window? It looks like a Mac.
Hide video.
Yeah, that's the one. Hide floating. No, you need hide floating.
Oh, it's
no hide floating meeting controls. That one. This one.
yeah. Sorry.
Okay. Okay, thanks, Echo. So I'm going to be moving on by talking about fluid inclusions now. So fluid inclusions are basically pockets of the exolved fluid that was trapped during crystal growth. So you can imagine there's a complete continuum between trapping a pure melt, that would be a melt inclusion without a vapor bubble, and trapping a pure bubble of fluid, that would be a pure fluid inclusion. And then there's stuff in between, and this is something we need to think about when we're dealing with melt inclusions. You could co-entrap a pocket of melt and a fluid, and if you were to then rehomogenize that or Raman it, you would end up with too much CO2. So you can see here, pure fluid, this one's trapped a little bit of melt, and obviously you could trap a lot more melt alongside. So we're going to talk about two types of fluid inclusions. Primary fluid inclusions, which are those that are trapped during crystal growth. These generally occur often isolated, so you can see there's just one or two fluid inclusions within these olivines, or sometimes they occur in these nice growth zones that you can see. We then have, We then have secondary fluid inclusions, which happen when you fracture a crystal and a fluid cuts across it and then it somehow heals up the crystal again. Exactly how that happens is a little bit uncertain with pure CO2 and olivine. You can see, for example, in this crystal, we have two cross-cutting like that, one coming in like this, and then a plane of fluids, which is basically parallel to the section. Exactly how these form, probably in a mush pile when you're exerting a lot of stresses, and that causes the crystals to crack. So how can we analyze these fluid inclusions? There are a variety of options. One of the main techniques is Raman spectroscopy. So what we basically do is shine a monochromatic laser into the sample. Almost all of those photons are scattered and they come out with the same energy that they went in with. But about 1 in a million of those photons is Raman scattered. That means there's an interaction between the energy of the incoming light and the vibrational modes of the molecule. And the molecule absorbs a little bit of that energy and shifts the light to a longer wavelength. And that is what we call the Stokes-Raman scattering effect that we're looking for. The key thing about this is that basically each gas species that is Raman active produces a distinctive peak position. So it's very small on this screen, but you can see, for example, carbon monoxide is at 2,143, SO2 is at 1151. So based on observing the locations of these peaks, you can work out which gases you have in your fluid inclusion. Now, not all gases are Raman active. A clear exception is things like chlorine species are not Raman active. And also your noble gases are not Raman active. So they will not give you these peaks. So we have a second technique that we can use to get those other species, and that is called microthermometry. How this works is you take your crystal, you polish it into a wafer, and you put it into a little heating and cooling stage. You can cool down to about minus 150, minus 190 degrees Celsius using liquid nitrogen. And then you progressively heat up that fluid inclusion and you watch the phase changes that happen. So you can see here, we start at room temperature in the top left. We then steadily cool it and you see this bubble is shrinking. We take it down to the coldest possible temperature. And then as we heat it up, we're looking for things like the temperature at which different phases dissolve, the temperature at which that vapor bubble ends up back in the liquid. And by linking this to extensive experimental work, we can work out which species are in our fluids. There's then one final method, which is laser ablation, where you basically just blast the inclusion. So I'm not going to talk too much about that, but you can destroy these as well. Both Raman and microthermometry are non-destructive techniques. So at least in volcanology, in recent years, a dominant focus has been on CO2. And this basically builds on the work that Echo was talking about. So volcanologists started with Lowell Moore and Matt Steele McInnes analyzing melt inclusion vapor bubbles by Raman. People then realized we can do the same thing for fluid inclusions because basically CO2 is a really special molecule. Most Raman active gases produce one peak. CO2 produces two peaks. And that is because there's two vibrational modes in the CO2 molecule which have very similar energy, and they perturb one another by this process called Fermi scattering or Fermi resonance. What we can see is that as we go to higher CO2 density, these two peaks get further apart. And that's mostly caused by that lower wave number peak shifting to the left. So by measuring the distance between these peaks, we can work out the CO2 density. Now, there's a problem with this, and that is that every single Raman spectrometer that we have looked at as a community has a different relationship between peak distance, that is what we call diode splitting on the x-axis, and CO2 density on the y-axis. So just to demonstrate this is a melt inclusion from Twin Lakes in the Cascades that was measured at Cornell. And Cornell have an instrument-specific calibration they developed with a gas cell. And you can see that will give us a density of 0.17 gram per centimeter cubed. If we used any of those other densimeters published in the literature, we would get up to 0.3 gram per centimeter cubed, so basically almost a factor of 2 error. So you cannot just take your Raman and take someone's calibration line and use it. That is going to generate up to a factor of 2 uncertainty. So what's the solution to this? This affects vapor bubbles and fluid inclusions. You can build a gas calibration cell. So Charlotte DeVitri was a grad student at Cornell and then came and did a postdoc with me. During her PhD, she designed this amazing gas cell calibration apparatus, where you basically have a pocket of gas that you hold under the ramen at a known pressure and temperature. Because we know the CO2 equation of state very well, if we know the pressure and temperature, we can calculate the density. You then measure it on your ramen, you get the splitting for one bit of gas, you then crank the handle, change the pressure in the cell, and you, over a course of about 24 hours in the lab, collect a calibration curve like this. What that means is for any unknown sample, you can basically measure your sample and get the CO2 density reliably. This is an amazing piece of equipment, but all of my gray hairs can be attributed to this, okay? Every single thing that could have gone wrong went wrong. We had to replace pretty much every single part because they have all these funny stickers saying, does not leak. They do leak, okay? The stickers lie. So what is the solution to this? Obviously, a lot more people want to do ramen than can spend $20,000 on a gas cell and a Charlotte as well. So in recent years, we've been developing CO2 fluid inclusion standards. So hexalamidrid has been synthesizing these. I've been working with natural samples. We've analyzed them on my ramen. We've analyzed them by microthermometry. We've analyzed them at Cornell. And we've just finished these 4 sets. So if you want to calibrate your ramen, ask for a set. We'll send you these. You'll calibrate your ramen and then you'll send them back again. So this should work. Okay, so why do we care so much about CO2 density? Obviously, for the stuff Echo talked about, it's crucial to get the total CO2 content of that melt inclusion. For fluid inclusions, it's actually even easier to get pressure from measuring the CO2 density. So basically, for a pocket of pure fluid that's trapped in a crystal, we assume it obeys Roeder's rules. The key one being there is no change in volume or change in mass. So if we have a fixed mass of CO2 and a fixed volume, that means we have a fixed density. And then using an equation of state, if we know the temperature at which our fluid was trapped, and we know its density, we can calculate its pressure. So for example, if you measured a CO2 density of 0.4, you could estimate a temperature and read off that you're about 200 MPa. And you'll be doing some of these exercises yourself in about an hour. And what you'll see is basically what this graph is showing. It is not very sensitive to temperature, which is great because you don't always know the temperature at which your fluid got trapped. So really, you just prep a fluid inclusion, measure it, and then you can get a storage pressure that quickly. And this has been really recognized as potential for near real-time monitoring. So it was a great paper by Vittorio Zanin. This was for La Palma. They actually did this using microthermometry. So their suggestion is you could have a van that you drive around your volcano with a microscope in the back, and you can get pressures during the eruption. Microthermometry really only works with this method when your magma storage is deeper than about 12 kilometers. So if you're shallower than that, you have to use ramen. You just can't see the phase transitions. And Charlotte did a nice exercise where HVO sent us samples in Berkeley. We prepped them and we got storage depths by the end of the working day. So this really can be a very, very effective way of getting depths reliably. But it only works in CO2 dominated systems. If you are in an arc, this is not going to work. And we can talk in the coffee break about why that is. So fluid inclusions can also give us insights into trapped fluid compositions. So there's a great paper by Thor Hanstein. They are looking at fluid inclusions from the Central American arc. And although chlorine species are not Raman active, they do change the melting behavior of fluids. Anyone who lives in a cold place knows this. This is why we spread salt on the roads. So they basically looked at the phase transitions of these fluid inclusions and said how much chlorine is in that fluid. So here's just some pictures of the beautiful fluid inclusions they had. And then they estimated how much pre-eruptive volatile contents they might have had. So do we have 1% vapor phase, 5% vapor phase, 10% vapor phase? And they looked at how much that might contribute to the total chlorine emission. So they said, for example, when we have a 5% pre-eruptive vapor phase, the exolved species already containing chlorine could contribute half of the chlorine budget of the eruption on top of what we would typically call the petrological method. So just one more example of how we can start linking these fluid compositions to degassing. Here is a graph of precursory SO2 emissions at Mauna Loa. This eruption basically started with very little warning. They knew an eruption was coming at some point. There was lots of inflation, lots of unrest, but the actual onset was seen on a webcam when the fire fountain started, okay? In terms of predicting that in future, this paper showed that there was actually 3 hours of precursory SO2 emissions that was detected by satellite that could have been used as a way to anticipate that eruption. At the time this paper was published, this was quite confusing. And that is because it's typically thought in Hawaii that sulfur only begins to degas in the final few hundred meters. So this would have required sulfur to be at like 200 meters depth 3 hours before the eruption, and an associated heat or seismic signal was not seen with that. So instead they said, you know, this is a possible way to monitor Mauna Loa, but it's completely unexpected. At the same time, we were measuring fluid inclusions from Mauna Loa in my lab, and we saw SO2 peaks. So we could basically say there is SO2 in these fluid inclusions. We can fit those using the area ratio of SO2 and CO2. And from that, we can generate a mole proportion of SO2. And basically what we showed is that this is pressure from the CO2 density, SO2 from the area ratios, and we are expecting sulfur to start degassing at about a kilobar depth. This is the degassing model everyone uses. For Hawaii, you can see it's predicting SO2 degassing way too late. For Echo's fabulous model, sulfur X, predicts the onset of sulfur degassing at about the right time for the right sulfur 6+ ratio for Mauna Loa. So during the exercises, you are gonna, if you have some extra time, have a look at the sulfur 6+ sulfur total ratio you predict, and from that, you'll be able to see what's happening. Because you can also see here that Kilauea is degassing later than Mauna Loa, and that is because it is less oxidized. So pay attention to that parameter if you have time during those exercises. And with that, we'll take any questions.
And we've got about 1 minute for questions. So I'd say there's always going to be time later on, right, for more discussion. So, but if we can just keep the time for now. Any questions? There.
So is Mauna Loa more oxidized than Kilauea?
Yeah, the sulfur Zanes data shows that. Mary Jo has some data showing up to like 40 or 50% sulfur 6+, which is actually kind of crazy oxidized. Yeah, surprisingly oxidized.
No? Okay.